The internet glance is so far away that it is catching light that has been traveling for more than 13 billion years. However, the universe has grown, and as a result, more light has been coming in. For the farthest worlds, we're considering back nearly to the Big Bang in time. The vastness of the universe might appear vast, but it began in its entirety from our reference to the singularity. Currently, this is how we might put the Big Bang theory in perspective. Anyway, the James Webb Space Telescope JWST has shed light on significant mysteries about the birth and development of the universe, leaving us speechless. Prestigious physicist Brian Cox has declared that the significant findings of the JWST could actually alter our perception of the entirety of the universe. Take part in exploring these brand new heavenly discoveries that promise to alter our comprehension. The James Webb Space Telescope, named after the well-known NASA director James E. Webb, stands as a wonder in current galactic investigation. This telescope represents a huge technological leap forward from its predecessor, the Hubble Space Telescope. Being the result of a cooperative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST surpasses the abilities of its predecessor. It makes use of cutting-edge technology and a design optimized for observing the universe in remarkable detail. Unlike the Hubble, the JWST provides concise and clear pictures of far-off heavenly bodies, primarily working in the infrared range. Its ability to penetrate astronomical debris and capture divine objects that were previously hidden from our sight is enhanced by its enormous 6.5-meter primary mirror, constructed out of 18 hexagonal sections. The JWST, unlike Hubble, is positioned about 1.5 million kilometers away from Earth at the second Lagrange point L2. It orbits the Sun in harmony with Earth, ensuring a constant and steady view of the universe while looking into the universe's farthest reaches. This involves traveling through light years and also entails a form of time travel. The JWST uses infrared instruments to observe heavenly objects and events dating back billions of years. The light emitted by these objects, due to the expanding universe, undergoes a redshift from the visible range to the infrared frequency or longer wavelengths. Fortunately, the JWST can detect infrared light radiated by heavenly bodies at high altitudes, empowering researchers to investigate the onset of stars, the universe's development, and exoplanet atmospheres. Its most recent historic discovery involves identifying an incomprehensible mass of cosmic systems at the edge of the observable universe. This finding casts doubt on the veracity of the idea of how things got started, provoking a reassessment of our key cosmological hypotheses. To better comprehend how we got to this point, we should take a short excursion through the history of space investigation. Ancient cultures, like the Greeks and Chinese, laid the foundation for understanding planetary movement by observing the bodies of the gods. In the 17th century, Newton's laws provided an imaginable structure for traveling through space. Midway through the 20th century, influential astronomer Edwin Hubble made historic revelations in cosmology and space observational science. His observations discovered that nebulae were isolated worlds far beyond the Milky Way, changing our comprehension of the size and expansion of the universe. Hubble's law, which he developed, demonstrated that galaxies farther out were moving away at higher rates, providing evidence to support the universe's expansion. Space history after World War II was marked by the beginning of the space race. The Soviet Union's Sputnik, the first artificial satellite in 1957, Yuri Gagarin's orbital trip in 1961, and the Apollo 11 moon landing in 1969 were crucial accomplishments. Jumping ahead to 1990, when the Hubble Space Telescope HST was launched, it provided exceptional clarity and amazing perspectives on the cosmos. The journey from ancient observations to the technological wonders of the James Webb Space Telescope shows constant improvement in our ability to interpret the entire world. It uncovered the boundlessness of space and changed fundamental thoughts in astronomy. Take the HST, for instance. It snapped the famous Pillars of Creation image in the Eagle Nebula, revealing a star nursery formed by huge columns of dust and gas. Another important achievement was the Hubble Deep Field, which captured a sizable number of galaxies in what seemed like a sliver of empty space. The HST also delved into exoplanet atmospheres, pinpointing components like water and organic molecules on faraway worlds, suggesting the possibility of habitable zones beyond our solar system. Following the development of the closest observed supernova, SN 1987A, it illuminated the life cycle of enormous stars. These accomplishments firmly established the Hubble Space Telescope's legacy as a foundation of modern cosmology with its dazzling, incredible discoveries. Its replacement, the James Webb Space Telescope, was launched to further develop the technological advancements and lessons learned from previous models. The most widely accepted theory of the universe's beginning, approximately 13.8 billion years ago, explains that the universe started as an extremely hot and dense singularity with rapid expansion, producing matter, energy, and underlying forces. As the universe grew, it cooled, resulting in the formation of atoms, stars, galaxies, and the various structures observed today. The Big Bang Theory also explains cosmic microwave background radiation, the vast scale, and the element abundance structure of the universe. Despite its wide acceptance, the Big Bang Theory faced skepticism and challenges in its earliest days. Alternative models, like the steady-state theory, proposed a universe without a specific beginning, and concerns about proof supporting the initial expansion of the singularity and observed anomalies arose. Most of these objections were addressed over time, and a significant piece of evidence came with the detection of cosmic microwave background radiation in 1965, aligning with Big Bang predictions. Space missions like COBE and WMAP, alongside further technological advancements, substantiated the theory. The James Webb Space Telescope, equipped with advanced infrared instruments, can examine cosmic dust. The JWST, working primarily in the infrared range, captures the most ancient light in the universe and observes objects formed shortly after the Big Bang. Its infrared abilities allow it to focus on regions where stars are made, celestial nurseries, and the formation of stars hidden from optical telescopes. Infrared light with longer wavelengths compared to visible light can pass through dust from other stars, overcoming a limitation of optical telescopes. The Hubble Space Telescope. The JWST is able to detect cooler objects emitting mainly in infrared, thereby making it ideal for phenomena research such as brown dwarfs, exoplanets, and faraway galaxies. As heavenly bodies move away, their emitted light waves get stretched, resulting in lengthening wavelengths or redshift in physics. The infrared capabilities of JWST can identify and capture these redshifted signals light from the early universe, providing insights into how it came to be and its evolution. Events that are active, like mergers of black holes or births of new stars, primarily emit in the infrared range, further expanding the JWST's ability to conduct investigations. The telescope can look into things that would otherwise be concealed or unnoticed. The JWST supplements optical telescopes like Hubble by having enhanced capacity to detect and be sensitive to ultraviolet light. This ability allows it to peer further into space and dig deeper into the past of astronomy, revealing hidden astronomical wonders and offering a more comprehensive perspective of the evolution of the universe. The JWST serves as a doorway into the previous phases of cosmic evolution. It recently disclosed something so mind-blowing that it might make you think twice about the entire model of the cosmology of the universe. We've discovered enormous, massive galaxies at the outermost observable universe. These ancient galaxies existed just a few 100 million years after the Big Bang, the cosmic dawn. The baffling aspect is that we don't know how such enormous structures formed early in the universe's history. This revelation might cause us to reevaluate our comprehension of the formation and the early evolution of the universe's galaxies. Studying early galaxies is important for deciphering the mysteries of cosmic beginnings. The JWST can increase insights into the way stars, galaxies, and planetary systems arose and evolved over billions of years. These suggestions also contribute to more general inquiries about the fundamental nature of the universe, including its composition, structure, and the forces governing its evolution. While the Hubble Space Telescope was groundbreaking for its time, it was limited in its ability to observe the early universe. Its primary restriction was its inability to effectively see through cosmic dust and locate the ancient light in the infrared range of galaxies. Older telescopes relied on ultraviolet and visible light observations, which made it difficult to examine the origins of the universe, where these wavelengths are absorbed or distorted by interstellar dust and gas. The James Webb Space Telescope represents a significant advancement in our understanding of galaxies from the early stages of the universe. In contrast, the JWST is able to observe predecessor celestial objects that formed within 100 million years after the Big Bang. Using its sensitivity to infrared light and the JWST's advanced imaging capabilities, it has uncovered an abundance of ancient galaxies, offering remarkable clarity and detail in understanding the evolution of the universe. Preliminary results from JWST have sparked waves in established models for the universe. Numerous aspects of prevailing theories are challenged by detailed data, prompting cosmologists to reconsider fundamental principles governing how we understand cosmic evolution and structure. Discrepancies between observed data and theoretical predictions have brought about intense debates within the scientific community. JWST observations have disclosed a greater number of galaxies in the beginning of the universe than anticipated by existing models that suggest a process of rapid and complex evolution. Early galaxies have been observed to be more developed than anticipated, challenging traditional models that predict slower development. The findings of galaxies' unimaginable mass challenge the assumed distribution and arrangement of large structures, revealing a cosmic web that is more complex and dense than previously considered. These suggestions raise fascinating questions and avenues for further exploration. The fact that large structures challenge early models of cosmic structure formation causes scientists to improve models for a more complete explanation. Understanding how such massive structures came together immediately following the Big Bang is a puzzle that calls for an explanation that doesn't violate fundamental principles of cosmology. Pronounced differences in the conditions of the universe's earliest days, in contrast to predictions made using existing models, have been revealed. These differences may indicate processes that were physically unknown before, unanticipated circumstances, or unidentified cosmic occurrences. In simple terms, these variations have prompted scientists to rethink and improve our models of the universe. Currently, all we can do is say that further exploration is required to include these unexpected observations into a more comprehensive comprehension of the universe. Initial observations frequently offer a more in-depth look at the universe than a glimpse. Sometimes, investigation reveals differences. For instance, early observations may reveal particular properties or arrangements within faraway galaxies, but closer examination reveals fluctuations in their composition, structure, or evolutionary pathways. In conclusion, massive phenomena are extremely intricate and require careful investigation for us to precisely comprehend their true nature. Spectroscopy, a method that helps discover the history and properties of celestial objects, is an illustration. It involves analyzing the light emitted or absorbed by celestial bodies. By examining the light's properties, spectroscopy provides detailed information about the chemical composition, temperature, density, and movement of celestial bodies. This analysis helps us understand the origins, development, and contributions of celestial bodies to the cosmic tapestry. The JWST has established numerous cases where initial observations were not the same as later investigations. For instance, initial observations of distant galaxies primarily suggested a straightforward structure dominated by lighter elements like hydrogen and helium, in line with conceptual expectations. However, spectroscopic examination with the JWST showed fascinating variations in defining elemental signatures, heavier elements or compounds previously missed or misunderstood in the universe. This challenges established thoughts on the origins of the universe's chemical composition and the mechanisms responsible for their development and dispersion over extensive distances. Similarly, initial beliefs regarding galaxies in the early universe were based on preliminary observations suggesting a relatively uniform pattern of organization and growth. However, more in-depth examinations by the JWST revealed a much more diverse collection of chemical compositions in these galaxies.